Hi, welcome to the Olympiad Geometry Club. Let's continue our study on geometry treasure. Today we're going to talk about Steiner-Lehmus theorem generalization, second part. In triangle ABC, DE are on AC, AB respectively. BD meets CE on P, and BD equals to CE. For any M that belongs to negative integer and 1, and for a real k if the absolute value of k is larger or equals to 1, and if AB to the power m plus KBP to the power m equals to AC to the power m plus KCP to the power m, then AB equals to AC. So for this problem, you can have a first guess that because M here is it's like an infinite group, which means that we're not going to really consider every case, right? So this one is pretty straightforward to manipulate because we can put the ABAC on one side and BPCP on another side. So let's consider the case that M is a negative number, which means we have, because M is negative number, right? So this is actually becomes 2 AB to the power m minus AC to the power m equals 2 KCP to the power m minus BP to the power m, right? And for this one, we can rewrite it as one to AC for here K times 1 to CP and 1 to BP. Yes. We can rewrite it as this way. So we know that now minus M is a positive number, right? Just to make it easier to think about. So minus M is a positive number, and for this one, it's obviously we can rewrite it as 1 over AB minus 1 over AC and times 1 over AB minus M, because this not minus M is a positive number, so we can minus 1, right? And plus 1 over AB minus 2 times 1 over AC plus whatever is the rest, right? You know, we basically just extend this one. Expand this one and all the way down to 1 over AC to the power minus M minus 1. So that's on the left side, equals to K times 1 over CP minus 1 over BP times 1 over CP minus M minus 1 plus 1 over CP minus M minus 2 times 1 over BP plus whatever the rest, all the way to 1 over BP to the power minus M minus 1, right? Now we can think about, we have this as our problem set, which means we need to use it. And eventually we want to prove something like AB equals to AC. We want to prove AB equals to AC, which means we just need to prove AB minus AC equals to 0. And here we got AB minus AC, right? We can rewrite this as AC minus AB 2 AC times AB and times, the rest part equals to K times BP minus CP divided by CP BP times, this part. So basically, we have this as problem set. We want to prove that AC minus AB equals to 0, which means we need to find the relation of AC times AB, CP times BP, and BP minus CP, right? And we already know that BD equals to C, but BP and CP, we have no information on it, which means that we want to find the relationship between BP, CP, AC, AB. That would make the problem more easier. Okay, so let's think about it. Now we look at the problem set. We only have that BD equals to CE, and we want to find the relation between BP, AB, CP, AC. That's kind of difficult. Let's do it this way. Because BD equals to CE, we move them, make a parallelogram. So BD equals to CE, so we can just passing through E, do a parallel line to the BD. Something like this, right? And passing through C, do a parallel line of BD. We have similar passing through D, do a parallel line for the CE. And this one is the same. Right, now let's give some name. For example, F. Let's set it as M. And Q. Okay. Now we want to find the relationship between F, M, N, Q, BP, CP, AB, AC. Right, we know that BD equals to CE, and we know MFQN is a parallelogram. So we know that MF equals to BD equals to CE equals to FQ. We know MF equals to FQ, right? And we want to find the relationship between MP and AB. We know that MP equals to ME equals to CN. Also, CP equals to QD equals to BN. So let's just, to make it easier, we set CN equals to X, BN equals to Y. And let's set the distance of BD equals to D. Okay, so we know that Cn equals to X, Bn equals to Y, and BD equals to CE equals to MF, FQ, QN, NM, right, equals to D. Now the question is, how can we calculate for the relationship between BP and AB? The first thing we want to prove is actually, let's find the relationship between N, F, and A. So let's do this. Okay. Assume NF, the line NF meet AB on a point. Let's call it H. And NF meets AC on a point R. Right? This point is P. Okay? So, what is H F to HN? HF to HN, we can extend this QF to this point. Let's call it S, right? So HF to HN equals to SF to BN, which equals to, see, HF to HN equals to SF to BN, right? So SF to BN, we don't know the distance of SF, but we know that SF is in parallel with MB, and because SF is in parallel with MB, and we know that this MF and BS, they're segments, so it's obvious the triangle SEF is similar to triangle BEM, right? So SF to MB equals to SE to EB equals to EF to ME. EF to ME equals to CQ to ME. CQ, right, because EF equals to CQ. So CQ to ME is actually CQ to CN, so CQ to X. And what is CQ? Let me see if I did something wrong. Oh, here, I did something wrong. SF to BN, yeah, let's rewrite this. I made a mistake here. SF to BN equals to SF to MB times MB to BN, right? Now it equals to SF to MB is EF to ME. EF to ME times MB to BN. EF to ME equals to CQ to CN times MB to BN. Right, and we know that CQ is D minus X and CN is X. MB is D minus y, and Bn is y. So A equals to d minus x, d minus y, 2xy. You can have the feeling of this symmetricity of this term, which means that we just calculate for the HF to Hn. Now we want to calculate for RF to Rn, right? Let me see if I have space here. Yeah. RF to Rn. Let's extend the MF meets AC on a point. Let's call it K. Okay. So RF to Rn equals to RK to RC equals to FK to NC. Right? So RF to Rn equals to FK to NC equals to FK to CQ times CQ to NC equals to FK to CQ, that is FD to DQ, times CQ to NC. And you can already see CQ to NC occurs here as well. And what is FD to DQ? FD to DQ, that is MB to BN. CQ to NC equals to D minus Y to Y times D minus X to X, right? So it's still D minus X, D minus Y divided by XY. Which means we just have the conclusion that HF to HN equals to RF to RN, which means HR are the same points, right? And what is H? H is the intersection point of line RF and side AB. R is the intersection point of line NF and side AC, which means AHR, these 3 points are overlapping, so that these 3 points are just 1 point, okay? Which means we can just redraw the figure as I'm not sure if I can make it better, but let's try. Yes. Okay. This is our new figure. We just proved that NFA are collinear, right? Q and this point is P. Cn is X, Bn is Y, and BD equals to CE equals to D. Okay. Why does it so important? Why do we want to prove that NFA are collinear? Because once we prove that N, F, A are collinear, now we can use X, Y, which is BPCP, to represent for AB. Right? Okay, let me write it down here. Now think about how can we calculate for the AB. Right? We can do it as AB squared using cosine law. AB squared equals to BN squared plus AN squared minus 2 BNAN cosine angle ANB. Right. So that's for the AB squared. And now we can see we know we know BN, and we don't know the length of AN, but it's fine. And we don't know the cosine angle ANB. Cosine angle ANB. But we do know that MNQF is a parallelogram, and also MFFQQNNM. Four sides are equal, which means MQ is perpendicular with FN. So because MQ is perpendicular with FN, the cosine of angle MNF is half of FN divided by MN, right? So it can be rewritten as BN is y squared plus AN squared minus 2y times AN times half of FN divided by MN, which is D. Right, that's a cosine angle A and B. So still we can rewrite it as y squared plus AN squared minus 2y AN FN to 2D. That's AB squared. How about it? Notice that y is CP, right? So we basically bring the CP already in this equation. And also for AC squared, it equals to CN squared plus AN squared minus 2CNAN cosine angle CNA, which is x squared plus AN squared minus 2xAN times cosine CNA. That's actually the same FN to 2D. Now the good news is that we have the AB squared minus AC squared. Right? We have AB squared and AC squared, so we can calculate for AB squared minus AC squared. Right? So let's set 8. This one as 1, this one as 2, so 1 minus 2. We can get AB squared minus AC squared equals 2. Y squared minus x squared, and minus 2y minus x AN FN to 2D, right? And 2 can cancel, right? So it equals to AB minus AC times AB plus AC equals to y minus x, y plus x. Actually, y minus x minus AN FN to D. right? That's what we have here. And let's just leave it with this one. Now we can come back to our problem set. Our problem set, let me just write it down. Our problem set is saying, now it's nothing new, right? I just write it down. 1 minus a, oh, sorry, 1 over AB2 minus 1 over AC. Yeah, times 1 over AB to the power minus m minus 1 plus 1 over AB to the power minus m minus 2 times 1 over AC. 1 over AC m minus 1. So I cannot write it fully, so here K times 1 over Cp minus 1 over Bp times 1 over Cp minus m minus 1 plus 1 over Cp minus m minus 2, 1 over Bp, and all the way to 1 over Bp minus m minus 1. Okay, great. Now think about all of this. So we have AB minus AC times 1 over AB times AC times, all of this equals to K times BP minus CP. No, should be CP minus BP, right? Because here I use AB minus AC. AB minus AC means that I already put a negative sign here. So BP minus CP, so need to put a negative sign here, okay? CP minus BP times 1 over BP CP and, this part, okay? Let's just make all of this part as Q. We can use Q to represent for it, right? Q1, and all of this part as Q2. That's fine, right? And for the equation we already have, excuse me, for the equation we already have, we need to think, now we can rewrite this one. So we have AB minus AC equals to K times CP minus BP. CP minus BP, which is Y minus X, right? So equals to K times Y minus X. Times Q2 divided by Q1. Right, that's what we have here as a problem set. And we know that AB squared equals to Y squared plus AN squared minus 2Y AN FN to 2D. Right. So if you look at the figure, we know that AN is larger than FN, right? AN is larger than FN, and D is larger than Y. So if you look at here, an is larger than fn. D is larger than y, right? D is larger than y, meaning that if we D is larger than y, so this term 2y, actually y a n f n 2d should be less than y a n f n 2y. No, it may make you confused why I'm going to do this. So let me explain. If you look at here, because y is, let's do this, y squared plus an squared minus y2d times an times f. Okay, that's easier to think about. An is larger. This one can be taken as an times an, right? So they both have an. Then we extract one an out. So an minus y2d an. Okay, sorry, fn. An is larger than fn, and d is larger than y. So this part is definitely larger than 0, which means this part is larger than 0, which means we just get a relation that AB is larger than y. Similarly, for AC, we have AC squared equals to x squared plus an squared minus x an fn 2d. So an is larger than fn, and d is larger than x. So we know that AC is larger than x. Okay, so now let's come back to our problem set here. We know that AB minus AC equals to k times y minus x q2 to q1. Right, and remember we have this equation here, so let's just replace. We can replace AB minus AC or we can replace y minus x, right? But actually for this problem we don't want to replace AB minus AC because we want to prove it equals to 0. So we need to replace y minus x. So we have y minus x here. Y minus x equals to AB minus AC times KQ1 to Q2. Right, so now remember we have all of these conclusions that AB larger than Y, AC larger than X, and we have this one. Now we put this one back to our third equation here. So you can see I'm going to put this one back to here. We get AB minus AC times AB plus AC equals to AB minus AC times KQ1 to Q2 times Y plus X minus AN times FN 2D. Right? Which means we can bring this to the right side. We have AB minus AC. Oh, we bring all of this to this side. It doesn't matter. AB plus AC minus. Let me think. Actually, let's move this out to here. So turns out to be Q2 divided by let me see, did I make some mistake here? I just feel that K shouldn't be on the denominator. Something wrong. Let me check. Where's the K from? K from here, that's correct. And then we got this one, that's correct. So we have that AB minus AC equals 2 K times 1 minus X. Yeah, I think that's correct. Which means 1 minus X equals 2 AB minus AC times Q1 divided by K Q2, right? So here should be KQ2. That's correct. Now we have AB minus AC times AB plus AC times KQ2 to Q1. Yeah, that's right. K and Q2 always together, right? Okay, sorry for the mistake. Now we have AB minus AC times AB plus AC times KQ2 divided by Q1, and then minus all of this, minus 1 plus X plus AN times Fn 2D. Okay, now let's think about this one equals to 0, right? Now let's think about Q2 and Q1. We know that the absolute value of K is larger or equals to 1, right? And what is Q2, what is Q1? We want to know the, which one is larger, Q2 or Q1. Let's go back to the definition. We set this one as Q1, this one as Q2. We already know that AB is larger than Y, right? So AB is larger than BN, which means is larger than CP. And also AC is larger than BP. AB is larger than CP. Remember here, minus M is a positive number. So 1 over AB is actually smaller than 1 over CP, which means all of them adds up should be smaller than these things, which means Q1 should be smaller than Q2, right? Q1 should be smaller than Q2. This is important. If you look at it here, Q1 is less than Q2. So Q2 to Q1 is larger than 1. K is larger than 1, right? So we can assume that K is larger than 1. The case K is larger than 1, and then we consider about another case that K is less than or equals to minus 1, right? So if K is larger than 1, that means AB plus AC times a number that is larger than 1 minus y plus x. We already know that AB plus AC larger than y plus x. So this part is larger than 0. And this part, of course, larger than 0. So which means AB has to equal to AC, because then the product would be valid, right, equals to 0. Okay, now what about the case that K is less than or equals to minus 1? If this is the case, we know that Q2 larger than Q1 is still valid. So this one should be this one, we can rewritten it as AB minus AC, right? The maximum of this one would be minus AB plus AC, right? Because we're trying to see the case if it can be 1. If this can be 0, right? Now this is a negative number minus y plus x plus an fn to d. Right? Now let's think about this one. Minus AB plus AC minus y plus x plus an times fn to d. Look at the figure. AB plus y is larger than an, right? AB plus y is larger than an. Also, AC plus x is larger than an, which means this one is larger. So minus AB plus AC, let's say this way, AB plus AC plus y plus x is larger than 2an, right? But fn, actually fn times an divided by d. Now let's consider about this one. So this one is larger than 2an, which means negative AB plus AC minus y plus y plus x is less than minus 2an, right? And fn times an divided by d. Let's think about that. Fn times an divided by d. Okay, if you look at this one here, NQ is a D, FQ is a D, right? So Fn should be less than D plus D, Fn should be less than 2d. Fn should be less than 2d. Right, so that means Fn times An divided by d should be less than 2d times An divided by d, which is 2An. That is saying if k is a negative number and the absolute value is larger than 1, this part is less than 0, which means AB equals to AC. Okay. So as you can see, this problem is not a very easy problem. You have to have a sense that we want to put, because based on this problem set, right, AB, BP, AC, CP. So you want to find the relationship between AB, AC, BP, CP. But BP, CP is kind of weird because it's just in the middle of the triangle, and it's difficult to find the relationship between BP, CP and AB, AC. That's why we move them around and make them triangles. Eventually we create some problem set as parallel lines or parallelograms, which we can calculate for the relationship between BP, AB, CP, AC. And then we just do the math with all the derivation, we get the conclusion. Okay, so I feel this problem is a very interesting problem just because it combines algebra and geometry together. It's kind of interesting. I mean, it's not really algebra, it's just some derivation. But it's kind of interesting because if you first time just saying something like this, you can easily get panic about it because you can easily think about, oh, how can I use this to in a geometry? In the geometry, you would never see something like 2 to the power 3, right? That's not in the plane geometry. But you know, for all of these higher order thing, it's always about to reduce the power and do the derivation. It's not really about the geometries, I mean the figure itself. Okay, I hope you like this video. If you think this video is helpful, please click the like button, comment, share, and subscribe to the channel. See you in next one. Thank you.